You, yeah. But I won't do that on the exam. I won't do that. Um, Let me go ahead and get started. So let's see. This is all arranged differently, and it's messing with me a little bit. Okay, so a couple things. Let me get the sign-in sheet started. I think every time I remember to pass the sign-in sheet, I feel it's like a personal victory. Like I actually remembered today, you know? What's that? Okay, so these announcements are very similar to last time. We have the homework due on Friday. Does anybody have any questions about the homework? I think it's a pretty straightforward assignment. Again, use E70 electrodes. Everybody all right with that? All right, so we have our exam on Wednesday, and class is canceled on that Friday. One other announcement, which I'll mention, it's going to seem a little vague because I really don't know anything past this. So I've kept it kind of vague because I don't know. There's going to be an event on the 15th on campus. It's going to be in the big structures lab, and there's going to be lunch. It's going to be from 12 to 1. I really don't know any more than that. So, but they're wanting like a lot of students. They're wanting like 200 students to show up. So, literally what I read is what I know. What? The X-ray laboratory? I don't think there's sentinels in there or anything. I know things. No, it's next Wednesday. 12 to 1. So I don't know anything other than literally what I just said. So, but if you should be free. So come, have food. You're as free as that lunch. Don't even. Not quite. Not quite. Let's talk about steel. It's I christen thee the Britannia or whatever. All right. Okay. Let's get into the world of steel. All right. Settle down. All right. Let's start going back to steel. So if you remember from last time, we started talking about column behavior, and we started off deriving the fundamental Euler buckling equations, for the load, pi squared EI over L squared, and then for the buckling stress, pi squared E divided by the slenderness squared. And then after we derived all that, we said, okay, here's why they're wrong, okay, or why they're not good enough. And we found that there were two really, really big reasons as to why they were wrong. Mr. Cruikshanks, give me one of them. Oh, yes, you can. All right, hold on. Give me one of them. Residual stresses, okay? Now give me another one. Oh, give me one. Give me one. The imperfections, exactly. Remember the fact that the member is not perfectly straight, or it might be out of plumb. There's your geometric imperfections. And the fact that you have stresses locked into the member affects its capacity. All right? Sound good? So the Euler buckling capacity that we derived is useful, but it's not good enough. Okay? So this solid blue curve right here, I really want you to understand this, okay? Because here's how you compute the capacity of a column. One of the things that matters when it comes to columns is its slenderness. The more slender a column is, the weaker it is. So as slenderness increases, remember slenderness is measured as L over R, or in this case, KL over R, because we want to be able to vary that or account for the fact that we might have fixed boundary conditions or pen boundary conditions or what have you. based on the slenderness, as slenderness gets larger and larger and larger, the capacity goes down. Okay? And what ends up happening is, based on the slenderness, we either have an elastic buckling scenario or an inelastic buckling scenario. Now, elastic buckling basically means that the column behaves like a rubber band. If you have really, really slender columns, you can load that column and it will buckle elastically. Essentially, it won't reach its Euler buckling stress. It will reach around 88% of its Euler buckling stress. The reason for that reduction is because of the presence of those imperfections, the fact that the column isn't perfectly straight or perfectly plumb. So we can't quite reach 100% of that buckling stress. We can only reach around 87% or 88%. Now that is for really, really slender columns. Most columns are of what I would call medium slenderness. Like that column right there is probably a medium slenderness column. And those columns are going to buckle inelastically. In other words, once they have failed, they're not going to behave like the rubber band and snap back into place. They're going to have some permanent deformations. So if you notice, the difference between, one of the differences between inelastic capacity and elastic capacity, elastic doesn't have the yield stress in it at all, but this one does. Because this, under inelastic buckling, it yields, so the yield stress obviously matters. Okay? Most columns that we do are going to fall in that inelastic range. So in terms of computing the capacity, once you get your slenderness, you would compute your buckling stress depending upon whether or not your slenderness is smaller or bigger than this limit, and this just comes from experimental testing and what have you, and then you can compute your critical stress. Yes, sir? That's the point on the line. So this is the slenderness value, right, or this is the slenderness axis, and this point right here is 4.71 square root of E over Fy. So if our slenderness is, if this is smaller than that term, we're in inelastic buckling. If it's bigger than that term, we're in elastic buckling. Yes? K is your effective length factor. Remember, it relates the pen column to something like a fixed or fixed free. Remember that? Okay. Now, for single columns, it's a lookup. For columns in frames, it's a whole nother story. So, but we will get to that in due time. Sound good? So, if I look at the capacity of a column, and I actually want everybody to open their manual and go to chapter E this time. So, an easy way of finding this chapter, if you go to, remember the shear lag table? Remember this, the table D3.1? Remember where your shear lag factors were? This is chapter D. Turn a couple pages and you'll be in chapter E. Okay? So I know the equation's on 16.1-33, but I'm actually on 16.1-31. The first thing that you'll notice is that the phi value for members in compression is always 0.9. And that's for everywhere in the chapter. Now, one very important guide that I ought to mention is the guide that's on page 16.1-32. Now, if you look, the guide that's on 16.1-32 has a bunch of different cross-sections. So, I-shapes and tubes and T-shapes and angles. And what that will tell you is, based on the cross-section that you're looking at, it will tell you what section of the code you need to be using. So if we're talking about just regular old wide flange columns, W sections, we're going to be in section essentially E3 or E4. And E4 really isn't going to matter as long as we have sections that are symmetric, which W shapes are. So we're either going to be in E3 or E7. Does everybody see that? We'll talk about what the difference of this means today. Okay, we will talk about that. All right, but I want to sort of soft pedal that for now. Right now, we're going to assume that we don't have any slender elements, so we're going to be in section E3. So our capacity is going to be F critical times the gross area. And how do we compute F critical? It's like this, and you can see it on that next page. If KL over R, or our slenderness, is less than or equal to 4.71 square root of E over Fy, this is our capacity. Otherwise, this is our capacity. Again, this is something I mentioned earlier. This Fy over Fe, it's not 0.658 times that fraction. It's 0.658 raised to that fraction. So you compute that fraction, and if that fraction comes out to be like 0.4, then it would be something like this number raised to the 0.4. Okay? And that equation just comes from going down to the lab and failing about 100 or 200 or 300 columns and recording all those stresses and mapping an equation that fits. So, but I do want you to understand that there's a sound theoretical basis behind it. Again, geometric imperfections and residual stresses. All right. Sound good? All right. Okay. Now, our elastic buckling stress is this term, this F sub E. That's the only one that's not shown up right here. I mean, we have our KL over R, which is our slenderness. E is 29,000 KSI. Fy is the yield stress. And then Fe is our elastic or our Euler buckling stress. Now, I didn't say that Euler buckling stress wasn't useful. It is used in the model that we use to compute the capacity. One point I'll mention, though, is make sure you're being consistent on your units. And we mentioned this earlier when we talked about tension members. If you have a 15-foot long column and you divide it by R that's in inches, your slenderness isn't going to come out right. So make sure that your units are all consistent. So express your column length in inches, okay, when you're doing the raw calcs. Does that make sense? Everybody okay with that? All right. Now, there's one other consideration that you have to mention, or you have to consider, and that's what's called local buckling, okay? Now, local buckling is essentially what I'm talking about, or what I was mentioning in this table, what E1.1 that listed the difference between non-slender elements and slender elements, okay? Everything we've been talking about up until now in regards to buckling, we've been assuming that the column behaves as one cohesive unit. In other words, when I load it and it buckles, the whole thing buckles, okay? That make sense? Well, that might not always be the case. In other words, maybe it's not the entire column that buckles. Maybe it's just a flange. Maybe just the flange buckles or just the web buckles. Now, I'm cheating a little bit with this image. Does everybody kind of see how in this image the column globally is fine, but locally the flanges have given up? Does everybody kind of see that? Now, I'm cheating a little bit in this picture because this had some thermal considerations that went on. This happened during a fire, so you know things heat up. The properties of steel tend to change. So, but it does give a very good example of what's going on. This image here down below, I will admit, it's kind of tough to see, but this is a column in a subway station, and you can see if you look that we have some local buckling that's happened right here along the flanges. Yes, sir.
The jet fuel fire?
You know, you're going to, now that you mention that, you're going to laugh. Well, hopefully you don't laugh too hard. I'm going to bounce one back at you. So this picture down here was a picture of a column in a subway station, okay? Now, where do you think this was? New York City. This was right under the World Trade Center. So that's not funny, yeah. So I'll be honest, I have done my best to try and find a better image of this column, and I for the life of me, can't find a better image of it. But this was a column that did experience that local buckling effect, but please.
So you think that on that
Oh, God.
no longer exists as well?
I'm going to have to, like, dump this recording. I have to upload it when we're done. He's like, you think? Yes, sir.
So global is on the left and local is on the right.
Let me put it like this. Are you okay with the understanding that this is an example of local buckling? Okay, let me go back a little bit. This is better. This would still be an example of global buckling. I mean the whole column going out. Now, what I'll say is this. A little bit of both is happening here because there's a little bit of global buckling, there's a little bit of local buckling. And let's also be clear that tends to happen. I mean, you start, loading these columns like crazy. I mean, they're just going to go. Okay. The question is, which happens first? Is it the local buckling or is it the global buckling? And that's what I'm going to try and answer now. Yes, sir. Well, because that was the one that saw the brunt of the load. Well, I mean, you're assuming that the load is evenly spread out. It's not a nice, pretty scenario. I mean, there was a few square blocks of rubble there. It's not a nice, uniform PSF. I mean, you see what I mean? I see what you're saying, but it's not that simple. There could have been a massive boulder right there. I don't know. So. What? Yeah.
Ignore that one. This one's not safe.
No, it's not. Oh, I like my job, so. Oh, God. Oh, God. I really want tenure, so I'm going to move on. Oh, good. All right. Back to steel. Okay. So what I'm going to do now is I don't want to get nuts into the math, and I may skim over this kind of quickly, but I feel like you all know enough about algebra that you can sort of follow along with me on some of this. But when we're talking about local buckling, for instance, buckling of something like this, we're not talking about the local buckling of a beam type element. I mean, remember when we did our derivation, we were assuming we had a beam that had some length L and some E and some I value, what have you. When we're talking about local buckling, we're not really talking about buckling of a beam, we're talking about buckling of a plate, okay? Now, plate mechanics is its own unique snowflake. I mean, when I was in grad school, I had a whole course in just plates and shells. So I'm not going to cover all the mechanics of plates and shells. I mean, we start getting into partial differential equations and series solutions and good stuff, really fun. I can see you all are already having a hard time containing your excitement over it. But what I do want to mention is a very fundamental equation that comes from plate mechanics, which is this. And this is the elastic buckling stress of a plate, okay? It's very similar to the elastic buckling stress of a beam. Like, here's our elastic buckling stress equation for a beam, and then here's the one for a plate. It's got a little bit more going on. For instance, we have our Young's modulus. We have nu, which is our Poisson's ratio. Y'all remember that from materials. And then we have B over T, which is just sort of a width to thickness ratio for the plate. Everybody okay with that? Now, this term K is kind of like an effective length factor, but it is really heavily dependent on the dimensions of the plate. And what happens is, if you start changing up the dimensions of the plate, you get really different variations on what K is. For instance, if I look at this curve right here, this curve A, this curve A assumes that this long side here and this long side here is clamped, so they're fixed end, okay? And if I start varying up the width to thickness ratios, these are the K values that cause buckling. Now, when you start getting into the math, and again, we're getting into some really heavy math, and I don't want to get too nuts into that, but as you start varying the slenderness of that plate, your K value starts to change. But one interesting little finding is that there's sort of a floor, like there's a lower bound value. Everybody kind of see that about the lowest value of K that you get for a fixed plate is about 7. Does everybody kind of see that? Like if this is 6 and that's 8, sort of about 7. Everybody kind of see that? So for different boundary conditions, you can find sort of a K value for the plate that'll tell you whether or not it's going to buckle or not. So if you start taking those floors, like I said, it was about 7. It numerically ends up being about 6.97. For fixed pin, for fixed fix, for fixed free, what have you, here's all these different cases of K. Now here's where they come into play, okay? What I want to do is I want to figure out if there's a way that I can check a flange or a web to see whether or not it's going to locally buckle. So before we get into the math, I want everybody to sort of turn to, let's turn to like chapter or section 1 with the W shapes. I want everybody to sort of turn to this. Like just any table in the W shapes. It doesn't matter. You know, like where the W13s are, 12s are, or 13s, 14s, 12s, what have you. Okay. That was, I said W13s are none. Okay, now if you notice, let's look at some of the dimensions that pop up on this sheet. I mean, you've got the area, the depth, the web thickness, flange thickness, and everybody's seen this. But what I want you to do is look on the page on the right. And notice how you have compact section criteria. Does everybody see that? And then there is a BF over 2TF, and there's an H over TW. Okay, what those are essentially the B over T ratios for the flange and the B over T ratios for the web. So let's see where they come into play. Now all I did here is I did a little bit of algebra and rearranged that to put everything all over onto one side. Okay. The reason why I did that is if you go through and do some math, just like with columns, you get a little bit of an inelastic transition at around, for plates it comes to around 70% of that value that you see on the x-axis. So I'm going to set that term less than or equal to 0.7. And I'm going to rearrange and solve for B over T. Now when I rearrange, this is just algebra. I'm sure you all could take this and take all this and put it over here. So E over Fy, multiply it over and all this and whatnot. If you notice over here, I've got pi squared, I've got 12, 1 minus nu squared. Remember Poisson's ratio. Poisson's ratio for steel is about 0.3. So you can plug and chug and determine this. This is actually a little more important than you would think, because what this tells us is if our plate reaches a certain slenderness value or not, it'll tell us whether or not the plate locally buckles. And it's the only thing that we don't know is this term K. Bless you. That's the only thing we don't know. Okay? So the way I'm going to handle K is I'm going to differentiate the difference between what is a stiffened element and an unstiffened element. So an unstiffened element is going to be an element of a cross-section that's only supported on one edge. So if I've got an I-beam, an unstiffened element might be like this portion of the flange because it's only supported on one side. Does everybody kind of see that? So that could be a flange, it could be a leg of an angle, it could be a channel flange, it could be any of the stems on a T-shape, any section that's only supported on one side. A stiffened element, like the web of an I-beam, that's supported on two sides. Does everybody see that? So we'll call that a stiffened section. If we're talking about a plate buckling, I think it would make sense that an unstiffened element is going to behave a little differently than a stiffened element. Make sense? Okay, so here's what we're going to do. Let's take a look at this dimension right here. So remember, we've got a W shape going in and out of the screen, right? So I think it's pretty safe to assume that this is, I mean, what do we have? We have fixed, pinned, or we have free, right? All right. I say that this is free, but what about this? Is this a pin support? Is that a fixed support? I don't know. For government work, what we say is we'll assume that support is not quite fixed, it's not quite pinned, it's somewhere in between. So we'll say that it's about a third of the way in between being fixed and being pinned. Everybody okay with that? I mean, like I said, there is no such thing as a perfectly fixed support or a perfectly pinned support, somewhere in between. Yes, and then you.
A third of the way between, which one's it closer to, fixed or pinned?
It's closer to the fixed end. It does offer a fair amount of rotational stiffness, but not infinite. No, that is a great question. I'm not saying, I think we're saying that it's more fixed than it is pinned, but it's not all the way. We got to reduce it down a little bit. And to give you kind of an idea, if you go back to those graphs that I showed you earlier, okay, remember, like, okay, let's take stiffened elements. Remember how this one was about 7, right? And this one's about 4. So what we'll do is we'll say 5. Actually, I got that backwards. It's on the other, and it's actually closer to the pen side. Sorry, I got that backwards. I'm getting sick. I think that's what it is. So between fixed free and pen free, we'll assume it's 0.7. So this just comes from those other slides, and we're just assuming it's somewhere in between. Right. Yeah, it actually is. Yeah, But let me also be clear, for most W shapes, this isn't a concern. I just want to mention it for stuff we'll talk about later. Now, if you take, let me show you something. Here's our base equation. If you take, let's take the unstiffened element. If you take K as 0.7 and plug this in here, you're going to get a value of about 0.557 square root of E over Fy. Everybody okay with that? And if you take the stiffened element, 1.488. Everybody okay with that? Now, here's what I want you to do. Notice, we got a little star. Okay? I want you to turn to 16.1-16. Okay? So, if you turn to this, you should see two big tables on either side of the page, and I'll give you a second to turn to that. What's that? That's you, dude. You're looking right at it. You just found it?
Yep.
That was a find. You found knowledge. All right. Now, one thing I want to point out, so we're focusing on the page that's on the left, okay? And read the title. Width to thickness ratios, compression elements subjected to axial compression. So this page on the left is going to be the page that we use for columns. The page on the right is what we use for beams. Okay, so pretty basic. Now, if you notice, it's kind of tough to see, but if you look on the very, very left-hand column, okay, notice how cases 1 through 4 are for unstiffened elements, and case 5 through 9 are for stiffened elements. Does everybody see that? So we obviously care about case 1 and case 5, okay? So if you notice case 1, I'm going to read this out, and it says flanges of rolled I-shaped sections, plates projecting, The limiting width to thickness ratio is B over T, and we'll talk about what that is, and then 0.56 square root of E over Fy is our limit. So basically, here's the long and short of it. So we're going to compute, we don't even need to compute the slenderness. We just take BF over 2TF, and you're going, well, why the 2? Okay? Here's the element that we're talking about. We're talking about width to thickness. So the width of this is not BF, it's BF over 2. So that divided by that is that slenderness limit. We just compare that against our limiting value of 0.56 square root of E over Fy. If our slenderness, like the one we look up in the manual, is smaller than that, what that means is that instead of our flange being really, really flimsy, we've got a really, really stocky flange, and that local buckling effect isn't going to govern our capacity. So we're going to find that this limit is going to be met for just about every column that we do in this class, but I still want us to check it. And the big reason why is for rolled shapes, I'd say local buckling isn't the biggest deal in the world. However, when you're doing something like a plate girder, which is very common for bridges or certain transfer elements in buildings, plate girders, instead of picking some shape out of the manual, you're actually saying this flange will be this big, this web will be this big, this other flange will be this big. You're actually tailoring the size of those flanges to meet your demand. So for rolled shapes, I'd say local buckling isn't a big deal, but for plate girders, it's a really big deal. So I do want you to at least be aware of it. So, sound good? Because we're talking about this element, and what I'm saying is this is B sub F, but this dimension right here is BF over 2. So this width divided by that thickness, that's where the 2 comes in. Okay? This element right here, we're not talking about D, we're actually talking about a dimension H. But again, let me be clear, you don't have to compute any of these, because like we just saw, go to section 1, they're right there. Okay, they're right there in the manual. Sound good? No, it's just because it's half that flange. Yeah. Algebra. Sound good? So here's the procedure for column analysis. If we've got a given column and we want to determine its capacity, the first thing we should do right off the bat is see whether or not local buckling governs. Okay? Now, let me be clear. If you fail one of these limits, it does not mean that if you put a feather on this column that the column explodes, okay? That's not what it means, okay? What it means is that we have to use a different section of the specifications. Go to that users table in Chapter E, and what does it say? If you have non-slender elements, which is going to be the case for us most of the time, we're going to be using section E3. I mean, read what the title of section E3 is. It says flexural buckling of members without slender elements, okay? What does section E7 say? Members with slender elements. So all it means is that if you have a section with slender elements, you just have to account for that. You have to account for the fact that local buckling is going to govern before global buckling. More often than not, we don't want that to happen, but if it does, it doesn't mean that the column is unusable or that if we place a feather on the column, it will explode, okay? That's the only point I want to make, because I think a lot of times if a student or even a young practicing engineer, they calculate this limit and they find it fails and they think, oh God, the column can't hold up, and it's done. No, hold on. It just means you got to use a different section of the spec. That's all it means, okay? Sound good? All right. Now, procedure for column analysis, okay? Now, my way of describing this actually comes from when I took steel design. The professor I had sort of mentioned this, and I thought it was a really kind of nice way of mentioning it. How many of you have ever mowed a lawn? Okay, all right. So I would say this method is your push mower. That's the one, you know, and just pushing it down. It'll mow anything. Just like that. This one will mow anything. Okay, it will handle any lawn, but it takes a while, right? Now this one is your riding mower, right? It's simple, it's easy, you just drive. But you can only use your riding mower in certain instances. Like you can't use your riding mower on a lawn like that, right? Got to be flat. This one's somewhere in between. This is like your self-propelled mower. This is somewhere in between. Kinda. Hard language, sir. Language. Okay. All right. All right. Going back to columns, my point is this. Unlike with tension members, the capacity was just 0.9 FYAG, and that was it. And there was no way to really check your work. What I'm suggesting is that there's 3 different ways to compute the capacity of a column that will all give you the same answer, plus or minus some rounding differences, okay? For instance, we're going to do an example where the capacity of a column is something like 900 and some kips. And we're going to get like 958.2 and 958.6 and 958.7. It's the same, okay? So these offer you a means to check your calculations not only on a homework but during a celebration. So you definitely want to make sure you're well versed in the 3 methods. Now the first method is to just use the equations. Just plug and chug. Do the math, okay? That's method number 1. And we're going to do an example where we use all 3, okay? Now, let me show you something real quick. I'm going to skip ahead and show you some tabbed regions, okay? Method number 2 is to use a particular aid in the manual. So we're tabbing like crazy today, I know. Method number 2 is to use table 4-1, okay? Now table 4-1 begins on 4-12. If you look at your gold tabs, it's right in the section that says COL for column. Let me be clear. This is one of the most important aids we'll use, not only for columns, but in the class in general. This is the aid that we use to design. This is the one that we use to pick a given column. A couple other things. There are some limits to this aid. For instance, right there, there's a big limit. The FY is 50 KSI. Okay? So if you have a yield stress that's different, can't use it. Okay? There's number one. Number two, this only works for W shapes, and specifically W14s, W12s, W10s, and W8s. And why do you ask that we're only looking at W14s, W10s, W12s, and W8s? Well, those four cross sections and all of the family of shapes that are in W14s, 12s, 10s, and 8s are the eye shapes that are the most square. In other words, the width to depth ratio of those shapes are fairly uniform. And that's really important because it makes your Rx and Ry fairly equal to one another. Yes?
There are other shapes in the valley, not W's, but for the E's and stuff. Someone have different FY values.
Well, yeah, and that's a good question. All right, that's a good point to bring up. Some of the other shapes, like the angles and channels and whatnot, have different strengths. For instance, Fy for the piles, what is it? It's like 42 or 46 or HP.
HP is 50, but HSS is 46.
46, yeah. So that's just because tubes come in fairly, they come in different preferred available steel than others. If you want to know where those yield stresses are coming from, go to this. Remember this guide right here? Remember this? Table 2-4. If you look, the W shapes are being reported with an FY of 50 KSI because A992, that's the preferred material spec. Okay? For tubes, what did you say for tubes? It was HSS rectangular sections are 46 KSI because we prefer to use A500 grade B 46. So does that make sense? That's where that's coming from. So the limit is that you can't use that for you can't use it for other grades of steel. Like if you had a tube that was grade 50, you'd have to just go through and do the math. That's what is normally produced. Yeah. The last point, or the last aid that I'll mention is, and we're going to go into detail on these, is table 4-22. Table 4-22 is at the end of the column section. I call these the KL over R tables. And all they do is they basically say, based on a given KL over R value, what is your phi F critical? Okay, so if you notice, like if you have a slenderness of 82, your and Fy is 36 KSI, your phi F critical is 22.7 KSI. That multiplied by the area, and there's your capacity. So it's sort of halfway in between. All right. Any questions? What's that? Yes, it is. We will be using quite a bit of it. Everybody good? Now I'm going to hop back a little bit because there's something I want to point out. So go back to method number one, and method number one is just using the AISC equations. I would argue that one of the most complicated aspects that's going to bug you all in computing a column's capacity is slenderness. In other words, if you get the slenderness right, I have found that 99 times out of 100, a student gets the problem right. Yes?
Here it's showing tensile strength.
You're probably in the wrong section.
Yeah, the next section. I was looking through it. Like, I mean, do we have to calculate all these things, or are those lookups too?
Good question. If you look,
It says yielding and rupture, like that's what we were doing.
all right, and you're probably looking at me like, why didn't we use that table, right?
Yeah.
If you look at the bottom, how did they compute the rupture capacity?
E equals 0.75. That's what we did.
No. The user note.
Tensile rupture on the effective net area of whatever yielding tensile yielding.
No, you're not seeing it. Hold on. No, I'm talking the area. No, wait. No, I'm sorry. I said look at the bottom. I want you to look at the top. How are they calculating the effective net area?
0.75.
That's the exact same assumption we made. Okay. Let me just say this. If you had used our equations versus using these tables, I'm just telling you, you wouldn't have saved a lot of time. Because in the end, All this would have done is allowed you to select a member. You still would have had to go back and check it. Okay? And let's also be clear, we still have that same limit. What if I gave you an angle that had 50 KSI? This wouldn't have been any good.
So like, if we were just checking the yield, curve section yield of like,
Well, that'd have been fine.
50, I could have just put 19.
But 0.9 times 50 times whatever the area is, that's not, that's why I don't use that table. In fact, in my opinion, that just should have even printed it, but that's just me. There's actually discussion on reducing the size of the manual. And if I had to guess, or if I hope, that's one of the tables that needs to be taken out, because there's no value to it, or no incredible value to it. It's simple. We could do that in Excel in a matter of minutes. So. No, I'm not. I don't think it. I think it would ultimately make your homework and exams take longer. That's really. I'm serious. So. Try to get me. Let me talk about this slenderness issue, because this is really important. Okay. For W sections, there's 2 radii of gyration. I want you to open just the W shapes. I'm having you all flip back and forth like crazy. Now, if you remember, there's Rx and there's Ry for W shapes. And if you remember when we did tension members and we were looking at W shapes, we always used Ry, right? And we always used Ry because Rx was always bigger. Remember, that's why we called them the strong axis versus the weak axis. Now, I'm saying that's the case for W sections. For something else, that might not be the case. But does everybody remember that? Okay. Now, think about it like this. If we have an I shape and we have a strong axis and a weak axis, which do you think is going to govern? Weak axis. Seems reasonable, right? My answer to you, though, is not always. Okay? Let me explain. Okay? Let's look at this cross section. Let's look at this column. So I have a column that has a fixed boundary condition on the bottom, and the entire column is how tall? It's what? 35 feet tall. Okay? Now, so what I'm saying is along the strong axis, I say it has an unbraced length of 35 feet. In other words, there's nothing preventing this column from buckling out, this way. There's nothing blocking it. Okay? So along the strong axis, it has a length of 35 feet. Is everybody okay with that? Well, that's the strong axis. Now the weak axis, does everybody agree that the column, it's going to be easier to buckle this way than it is that way? Is everybody okay with that? Now, the weak axis, it's not the same story. With the weak axis, I got stuff in the way. I've got, an element here and an element here. Probably those are beams framing in, right? This column would be something you'd be very likely to find at something like a hotel, and you go into the lobby, and the lobby can sometimes extend over a couple floors. So this is one of the columns, let's say, in the lobby. Here's the second floor of the hotel, here's the third floor of the hotel, and here's the fourth floor of the hotel. But out here's the lobby, so you've got that one column that's being braced in one direction, but not in the other. Does that make sense? Am I okay with that? So let me ask it like this, okay? The longer a column gets, the weaker it gets. Is everybody okay with that? What I'm saying is that this column has different lengths in different directions. See what I mean? Along the strong axis, it has an unbraced length of 35 feet. But in the weak axis, we actually have 3 different segments. We have a 10-foot segment, a 15-foot segment, and another 10-foot segment. Each one of those segments has different boundary conditions. For instance, this one here on the bottom, we might say that that's fixed, and we might say this is something like pin. So this is a fixed pin segment of 10 foot long. This is a pin segment that's 15 foot long. Everybody kind of see where I'm getting at? So each segment has a different slenderness that we then need to check, and the largest KL over R is what's going to govern. Yes, sir? Yeah. Mm-hmm. Mm-hmm. Yes, you're exactly right. In fact, what we would do is we would take this column and we would divide it up into a model that looks something like this. So I've got here an image of the column in the strong axis. So if you notice, this is the column that's wanting to buckle like this. So you can see here's the flanges, and we're talking about the column buckling, this way. And in that direction, all we have is a fixed pinned column that's 35 feet long. This symbol right here is trying to illustrate what the column really looks like. If I was looking at the column like this, I would see a flange, and then that's the web. Does everybody see what I mean? Okay, that's the column in this direction. In the other direction, I've got fixed, pin, 10, 15, 10, and what I am seeing is the flange, but then these two dotted lines right there, does everybody see those? That's the web. So you got the flange and then the web sort of behind that. Everybody see that? Everybody okay with that? Okay. So what we're going to have to do is check each of those sections. So I'm going to get a KL over R for this, a KL over R for this, a KL over R for this, and a KL over R for this. Each one of those KL over R's, whichever one is the largest, that determines how strong the column is. Okay? Does that make sense? So speaking of, why don't we do this example next time? So this example, let's just be clear, we have a W14 by 90. Its Fy is 50 KSI. There's the strong axis bracing. There's the weak axis bracing. What we're going to do is when we come in on Friday, we're going to attack this problem. We're going to do it 3 different ways, okay? We're going to look at the, we're going to look at the, using the equations, the push mower, using the riding lawnmower, and using the self-propelled mower, okay? And we'll see that we'll get the same answer, plus or minus a few decimal points. I mean, let's be clear. If you've got a column that can hold up 958,000 pounds, hopefully the 0.1 or 0.2 kips isn't affecting your design very much. And that really won't be the case because of the discrete nature of column design. I mean, the rounding matters and the decimal accuracy matters, but not as much as you would think. And let me just make sure everybody's clear on where we're headed. Once we understand how to analyze a column, we'll be able to design one. So after we do this example 3 different times, we'll go through and design columns. And our design aid is going to be, bless you, going to be using the riding lawnmower, table 4-1. Everybody good? Homework's due on Friday. I will see you all either on Friday or in 10 minutes. So, all right, we'll see you.